Perfect. So you're ready to go, Paul?
Yeah, thank you. Hi, everybody. My name is Paul Albertella. I work for Codethink, and I'm the chair of the OSEP working group at ELISA. And I'm going to be talking about the RAFIA approach. What is it? Why do we need it? How we've been using it in ELISA, how I've been using it in work with Codethink, and how the overall approach is being refined, and where I'd like to go with it next. So the motivation for RAFIA is really about the perceived challenges of using free and open source software in safety. When you're trying to follow the guidelines or to meet the criteria in the safety standards, it's hard to map those to the way that open source software is developed and the way the work is managed. It doesn't follow the reference processes that you see described in the safety standards. And this is because FOSS communities, by and large, don't operate like commercial organizations, and they don't implement things like quality management processes, let alone safety processes. There's some exceptions to this, but these are kind of the general perceptions, and they apply in particular to Linux, which is our focus in ELISA. The work on this software is not commanded or directed by a central authority, so they're not working towards a particular goal. They're not trying to produce a product, and the contributions that people make are voluntary, so we can't actually ensure that people are going to work on a particular feature or a task. And there's often explicitly no one to take responsibility from a legal perspective for the software if it doesn't do what you expect, because it's declared not fit for a particular purpose. And it's not developed for a specific purpose. It's actually developed for other people to use for a wide variety of applications, and in a way that values rapid iteration over producing something very specific that we know what it is and why we're making it. And the development models that are applied by open source software projects can be informal or inconsistent. They may have examples of good engineering practices, but they rarely follow the kind of processes that the safety standards expect. Now, it's important to say that this doesn't apply to all open source projects. There are some open source projects that make a real effort to address some of these, but this is kind of the general challenges that we're facing. So how do we meet these challenges? So there are some guidelines in the safety standards for how you use pre-existing software. The ISO 26262, they're specifically looking at extending these, which was talked about in a previous presentation by Gab. There's some guidance in IEC 61508, and there's a concept of software of unknown provenance in there, 62304, which is for medical devices. But even if we follow this kind of guidance, we still have some specific challenges to address with open source. We need to actually understand how the components that the FOSS components we're using are configured and constructed in our particular system, because they're intended for a variety of different uses and purposes rather than a specific one. If we've got some particular needs for the purpose to which we're using the software, we need to actually understand what those are, because we don't have them specified for us by the open source software usually. And we want to understand what these are so that we can actually verify that it's doing what we need it to do, both from a safety perspective and from a functional perspective. And we need a way to validate those assumptions, to actually make sure that, you know, even though we're verifying them with tests, that they're actually achieving what it was that we wanted to do. And because we're with open source software, we're often expecting to incorporate new changes because of this rapid iteration approach. We want to actually understand how we're going to incorporate new changes from mainline. the software that we're using. So the approach that we came up with at Codethink for this was something that we talked about in some detail at a previous ELISA workshop. I'll summarize it very quickly here. I really want to talk about how we're applying it rather than going into too much detail about what it is. Essentially, it's got 3 components to it. The first is about using top-down hazard analysis to understand the risks with using the software and to derive some requirements for it. And part of this is about actually coming up with what I've described as an inferred design, what we're expecting the software to do, what assumptions we're making about it, and how those responsibilities actually map to what we're using it for, in particular to our safety requirements. The next part of it is automated construction and testing. This is important because we want to be able to control this, control changes that we're making to the software by incorporating updates from mainline. So we want to be able to automate that to verify that it's continuing to meet our requirements, and also so that we have a controlled environment within which to do that verification. We're understanding all the components that affect that, which will include the tools that we're using to build the software as well as the software itself. And because we want to also validate that those things are achieving our actual goals, we also want to use some other techniques, in particular fault injection. And I'm talking here specifically about software fault injection, which might be as simple as making a one-line change to a software component to deliberately break it. And the reason we want to use this is to show that the tests that we're using in our automated verification are actually detecting when the problems occur, but also because we're not just using this software in isolation, we're using it as part of a system, and that system is likely to contain some other safety mechanisms. We want to be able to break the software in order to show that those safety mechanisms operate and achieve the overall safety goals. So Codethink used RAFIA for a concrete example, which was a tool qualification for an integrated set of open source tools, which was called deterministic construction service. And this is about producing verifiably reproducible construction of complex safety critical software from a set of controlled inputs. We used Stpa to define the safety requirements for this, to identify how the various integrated tools interacted with each other and how that could lead to hazards that would lead to the losses that we'd identified. The losses in this case being uncontrolled changes that might then get deployed to a production environment. And then on that basis, we could define constraints that needed to be satisfied to prevent or mitigate the hazards that we'd identified. And those were then used to implement tests that we could use to show that we were continuing to meet those requirements. And also fault injections to show what happens when those requirements are violated, to make sure that our tests catch them, but also that the mitigations built into the system actually operate to detect them as well. On a simple level, if we actually have a build failure as part of our construction process, do we detect it? Is it visible to us? And can we then take the sort of reaction that we need to deal with that? Now, the requirements that we've generated weren't just requirements on the sort of software components. They were also assumptions of use, which are documented in a safety manual, so that end users using this tools integration would know what requirements they had. And all of this was constructed as part of an automated process. So it was both implementing a controlled environment for that process and verifying that process was controlled. And to do that, we were using the concept of binary reproducibility to make sure that if we did have a change introduced, we could detect it because we can actually see the change on the end binary. So this was as an example of using RAFIA, and on that basis, we had some confidence in the approach, and so we've actually been starting to use some of these this approach in ELISA. One place where we've been doing that is in the OSEP working group. We spent some time using Stpa to analyze stack memory, looking at it at a system level. So as you can see from this diagram here, we're actually considering not just the actual operation of the components on the system itself, which is in the grey box, but also the external components that lead into that, such as the compiler that you're using to build some of those components, and the way the system itself is constructed. We also had some presentations from the Hawaii participants who you'll have seen in the previous, you may have seen in the previous presentation, talking about the Stpa that they were doing for dynamic memory, which was framed at a different level. So this was looking at safety requirements on the kernel specifically, and actually understanding what it is we needed the kernel to do in order to meet some particular requirements. And you know, an example of that would be an example of a loss or hazard is if the kernel stops responding to an external input, then we need to detect that behavior and take measures to restore the system to its operational state. So this is focusing on the kernel rather than a wider safety system. We've also been using Stpa in the automotive working group. This was looking at the telltale use case, which quite a lot of work had already been done on that, and some safety requirements have been documented. But there'd been some work to look at to develop a new safety concept. And so what we did was apply Stpa to that new safety concept in order to try and refine it and to clarify what the requirements were for it. And in the process of this, we kind of experimented with some different ways of approaching the control structure. We started by trying to actually have the operating system as one of the controllers in the diagram and understand what what the interactions were with it. But that actually made for a very difficult control structure for us to parse. So we ended up actually not having the operating system represented on the diagram and just focused on the functional blocks, and then understanding the role of the operating system by looking at those interactions. We've got to the state where we have a control structure that we're happy with, that makes sense. We're actually got a working session on this tomorrow as part of this workshop. We'll be very much welcome some more input from people who can join that session, and also from some contributors in the working group itself. We just got to the stage now of looking at unsafe control actions on the basis of this control diagram, and then that will lead us on to documenting both refining the safety concept and documenting our requirements. Another way that we've been Codethink have been refining the RAFIA concept is looking at a different use case. It was a demo system for a rear-facing camera concept that we created for a talk at the Automotive Linux site, using a Raspberry Pi with a camera and some simple push button to represent a gear stick, which would indicate when reverse gear was engaged, which was the point at which we would start showing the rear view, the view from the rear, displaying the rear view camera on our display. And also we had a warning light LED, which was going to be lit when we actually detected a problem. The idea being that rather than trying to create a system that was that we could kind of guarantee was safe, we wanted to understand where the risks were and how we could detect those risks and indicate them to using this LED. The idea here was to have an easy to understand example of a mixed criticality use case, but we also wanted to in particular look at when you have a large and complex non-safety workload, how you actually might approach controlling interference between that and the safety application. And we actually used AGL's reference rate IVI to provide that non-safety workload, and it was used a relatively simple system management concept and a container using C groups to control the access from AGL to the devices that were important to the safety application. And again, this was a way of exploring the strengths and limitations of the features rather than to come up with something which we could declare safe. So again, we were using the control structures as the beginning of this for Stpa. We started with a look at the wider system context, so looking at the user's interaction with the hardware components and that their interactions with the main platform itself on the Raspberry Pi. And then we focused in on the operating system context itself. And here we were looking at the safety applications and the non-safety applications, but also at the operating system abstractions. So in other words, the parts of the operating system that are actually responsible for managing the interactions with the hardware. So we used this in a couple of ways. One was to actually refine the safety concept. So we came up with the initial demo, we came up with an initial implementation of it. We did the hazard analysis to identify where there were risks, and then we refined it. And one of these was actually in the use of the compositor. So the compositor is used to actually handle the display of various views, various windows on the physical display. The idea was that the rear-facing camera application would take over that display when we were in reverse gear, so we didn't want anything in AGL interfering with that. And we identified one problem with that, which was that you could have an application within the AGL container could inadvertently have the same prioritized ID as the camera application, which means that it could overlay the camera application's view. So we added a proxy compositor to make sure that it had no way of could have no way of doing that. That was the only thing that the applications within the container could interact with, and therefore there was no way they could inadvertently override the camera view. So the other thing that we were looking at with this was having developed a set of requirements, how we could set about testing those and how we set about developing fault injections for them as well. Because one thing to do this analysis, the next thing we wanted to explore was how you actually apply that to a system. And there were a number of aspects that we looked at with this. One of them was actually about tracing from our requirements to the tests. With Stpa, you end up with what are described as constraints, the idea being that they're something that you can verify in your system directly. So in theory, that's something that you can run directly using something like the arrange, act, assert pattern that you see with testing tools such as testing syntax such as Gherkin. The idea being that you have a definition that says, in this circumstance, with this action, I expect these results, and that's what I want to verify. That's something that everyone can understand. The people developing the system, the people verifying the system can all read that because it's in a straightforward English. But then you can actually use that to run the test by developing testing fixtures and a testing framework that operate on those definitions directly. And because the definitions are use a kind of logical syntax, it's straightforward and unambiguous. And also you can reuse some of those test fixtures with different tests where you have a similar setup required for the test. The other thing we looked at was at implementing system level tests, because I think the focus that we've had certainly with this is testing at the system level, because you're wanting to test not just the operation of the individual software components, but those components within a system. And for that, you're going to want to test on hardware, but you might also want to do some tests in virtual machines or containers, really for the purpose for speed, so that you can do a level of testing with for a new update, for example, before you then deploy it to hardware, which you might have a limited set of. And this needs not just ways of managing the deployment of those tests and the building of the different test environments, but also monitoring components that you have within those environments, so that you can make sure that everything's happening. And because you actually want to be able to have confidence in the whole thing that you've tested, that may mean integrating some of the monitoring components into your deployed software, which, safety context can actually be very useful anyway, because producing diagnostics that you can use to measure the effectiveness of your safety measures is always going to be desirable. Then there's how you actually derive fault injections based on the loss scenarios that you've identified through your Stpa analysis. And some examples that we came up with for this particular demo were if you want to understand whether a process within in AGL within the container is consuming too much CPU bandwidth, does the mitigation that we've got for that actually prevent that from swamping the CPU and preventing the camera application from operating? And similarly, the problem that we identified with the compositor could, if we had an app within AGL which had the same ID as the rear-facing camera application, would that actually compromise it? So we were able to test the design update that we made and show that that was working. And then the final thing that we've been looking at is, actual online verification measures. So not just testing that it works in your development environment, but when you have a deployed system, can you monitor the behavior of the system and detect when it might have been compromised? And an obvious thing to do here is actually kind of monitoring the frame rate of your camera to detect whether that's being compromised by something else that's happening on the system. So that was some useful exploration of some of the concepts that we'd identified in RAFIA. One of the other things that we encountered through doing this was actually the need to clarify the Stpa methodology itself. The team from Hawaii talked a bit about the approach they took to this with the dynamic memory in the previous presentation. One of the things that we focused on were really just kind of documenting the guidelines with a clear focus on software, because as the actual Stpa manual is largely focused at a kind of a higher system level, and talks about concepts such as actuators and sensors, which make perfect sense when you're dealing with hardware, but kind of concepts that it's not easy to map directly to software. We discussed this with John Thomas, who's one of the Stpa Handbook's authors, to better understand it, and we've been going through a process of creating a checklist of scenario types that are useful to consider when analyzing software systems. And one of the things that we came up in the discussion with John as well was this fact that there's a lot wider interest in Stpa in general, which is kind of leading towards ideas about standardization. The Society of Automotive Engineers, for example, has published a set of recommended practices for applying Stpa in automotive. And there's some discussions about creating a formal standard with another international standards body. But yeah, the sort of question came up was, would it actually make sense to create an open source project to develop this Stpa documentation, and in particular to develop it for use in software? So I'll be interested to see if some of the other participants in ELISA would be interested in that as well. So where next with RAFIA? So there's still lots of opportunities for us to explore it and refine it within ELISA. I'm certainly planning to continue to discuss it in OSEP. We have a goal that's been defined by the TSC to publish some, I think what's described as a meta level instruction for safety analysis. In other words, a set of some overall guidance about how to set about doing safety analysis, and it's possible that RAFIA could be a basis for that. We also have the question about how we apply Stpa. Do we apply it to generic operating system features at the low level within the kernel, or do we actually focus on specific system use cases? I think there's some interesting things to be learned about in both cases, but I think one of the things that we found trying to apply it to generic OS features is that we actually often get lost in the what ifs of you know, what about this particular edge case or that particular circumstance, rather than focusing on the safety part of it within a concrete system. And the other big question is can we, by following this method, provide equivalent confidence for integrity versus the standard approach that we see described in the safety standards. We're also going to continue to do the Stpa within the automotive working group. We definitely need some more input and some contributors to help with that. I hope some of you will be able to join the working session tomorrow. And also we could potentially build on that to explore the tests and fault injections in this context and develop those for the telltale use case. I also want to align with the medical devices working group. They've been using Stpa for a couple of years now, looking at open APS, taking a slightly different approach to it, but I think they've learned a great deal, and I think it'd be really useful to share the different things that we've learned from applying Stpa in different ways. They've also been using kernel trace to inform and complement that safety analysis to kind of get that connection between the high-level safety analysis and how that actually applies to the kernel. So it'd be useful to explore that as well. And I can also see some possibilities to collaborate with the tools working group as well. If we kind of explore the test automation and fault injection tools and strategies that are out there in the open source world, I think that might be a really valuable thing to do. That's it for my presentation. Do you have any questions? I can see Shu has asked about system and use cases. One of the things we discussed in another earlier session was whether we needed a wider set of use cases, and whether a system use case from the industrial or the IoT world might be helpful. I think, again, I certainly think applying this RAFIA approach to actually, if not concrete systems, at least more concrete system use cases, certainly seems to give us more benefits than trying to think about very generic operating system concepts. But at this point, I think I'm interested in looking at both to see what we can learn from them.
Thanks, Paul.
Any other questions?
One follow-on question. When you use the RAFIA approach, do you use, is that approach overall system and use case, or would you break it down to analyzing the system first and going to the use case? Aren't they combined, really?
Yes, they're really the same thing. So I kind of talk about system versus use case. Ideally, you want to be applying this to a concrete system, because the hardware that you're running the software on and the other hardware and software components in the system are all part of our safety analysis. But I think if you're trying to for example, develop a set of requirements that you could apply to a number of concrete systems, then you might look at a more abstracted system use case. So that's when you kind of talk about a use case rather than something concrete. But you can apply Stpa certainly to whatever kind of abstraction you like. I think certainly what we've learned is that applying it to something more concrete is almost always better, simply because it means you spend less time on the what ifs and trying to guess how it might apply than when you actually got something concrete to look at. And that concrete system doesn't have to be an implemented system, although that actually can be very helpful. It could also be applying it to a system architecture in the first instance, and then using that to implement a system, and then refining that system architecture as you learn more about it.
Thank you.
Any other questions? So
no question, just a comment that this seems like a reasonable thing to start doing, and I agree with it. Let's use this as potentially a starting point for that general guidance. Try to see if we can do that for that action item we've got from the TSC side. So I'm +1 on trying to work from this approach, see how we go.
okay, great, that's good.
I can't see any drawbacks anyhow. Does anyone else see any drawbacks or a problem?
No, I think that's a great idea. Starting to use this tools as a starting point and see how far we can go with it. Okay.
Is there people that are interested in starting to work on the how to break down a problem and start working on that white paper? We've got a couple names from the prior meeting, but is there anyone else on this call, for instance, that's interested in this topic, that wants to be part of meetings and rough work that's starting up? Okay. If we create this, is there someone that's going to use it? Let's put it that way. Is there someone on this call that wants to use this? If we actually had it, if we had this written, would they basically be willing to review it and give us feedback on it if it's useful? Feel free to put comment in the chat. Just trying to get a feel for, is this interesting or not to others as well? Okay, and then Sudeep's wanting to help from the tools working group. Thanks, Sudeep. And automotive is interested too. Actually, Philip, one of the things I was wondering is, does it make sense for the automotive and the medical devices working group to have some sort of joint session to talk about our Stpa approaches at some point in time and do that sort of compare and contrast and just sort of see where the common highlights are?
Yeah, I guess you're much further than we are with your level 2 to level 3 migration, and we are still trying to understand what it really is. But bringing us a lot of discussion. We are level 0. But anyway, maybe we can learn more from you and just give the right question back to yours. So yeah. Let's put it as an action item right in the minutes to just
set up a joint call.
Set up a joint call for Stpa between medical and automotive.
Stpa, or just set up a special, maybe use one of the alternate CSC ones to just invite everyone who wants to come talk about Stpa approaches. And we'll use one of those as a way of doing a bit of a retrospective on what's been working, what's not been working, and and see if we can come up with some better ways of representing how we're conveying this information. That's been a nice like I say, I think we've got a lovely complicated spreadsheet that Milan has been awesome about working us through in the medical devices side that might be useful. But the question is, how do we basically put it into GitHub in some fashion that's effective for people?
Yeah, and that's something that we can definitely talk about, because I've got some ideas about that.
Okay.
The other thing I'm really interested in is the Stpa is great, but we're doing it for a purpose. I really very much like to actually see us applying the outputs of that Stpa, which is why sort of the testing and fault injection stuff is really good. The tools working group can help to sort of enable that by sort of providing us environments within which to run those tests. But in the end, actually coming up with the tests and the fault injections is the next step. I don't know whether that's something that makes sense in medical devices.
Well, like I say, our community has their own tests and test infrastructure, but they really haven't, some of the system level issues. You know, I know that like Milan has stumbled into the whole dependency hell of installing it and working through the various things, and they really haven't tackled that as a community, but that's a whole system-wide issue in terms of the whole ecosystem-wide, I probably should say, where, you know, we've got multiple pieces of software we're trying to update as we move forward, and then, you know, they've got their various tests there. Now, possibly what we can be doing is helping them add tests, but there's also some issues that are outside the scope of what they care about, which is their algorithm, that are system-wide that we need to figure out somehow. You know, what are better ways of tracking this and so forth.
Yeah, I mean, that's it. I think it might be a valuable example of, you know, we're not focused on the actual safety application itself, because that's, you know, the focus of that is on their algorithm, but on the system integration angle of it, that actually might be valuable for other safety applications using Linux to understand. And similarly for the automotive one, we have an implementation of the Telltale. I know that the one we've been analyzing is actually, we don't have an implementation of it yet because it's still at the safety concept stage, but I think if we could get other contributors working on implementation, developing some tests for that in parallel with that, and some fault injections would be really interesting.
Okay. Well, I guess let's figure it out from that perspective. I think we're we're over a little bit over time at this point. I'm not sure, but it seems promising. So hopefully someone's captured this in the notes, because I was talking, so I suck at talking in notes at the same time.
Well, I think, yeah, we can kind of follow up on this list I've got in the what next, in the TSC perhaps, be useful.
Sounds good.
Yeah, I don't think we're over time because I rattled through my presentation fast.
Oh, sorry.
It's all right. But yeah, happy to leave it
Does
there.
anyone else have any comments? Thanks, Philip, and thanks, Paul, for thank you, Paul, for the good session, and thanks, Philip, for being let's collaborate on the automotive and get that going with the analysis.
And I put it in the minutes and action items so we don't forget about it.
Excellent. Thank you for your help there.
Thank you.
Okay, so I will stop recording now then. Okay, so thank you very much, Paul. That was indeed very interesting, and you know, look forward to see how it evolves. Okay.